Welcome to this network analysis class. In today's class, we will talk about uh, higher order differential equations. Higher order differential equations. So these equations are usually of the following form: some constant a naught d square I by dt square plus a1 di by dt plus a2I equals to 0. So this is a second order differential equation. Okay, this is a second order differential equation. So if you take a look at this problem, the solution, that is the value of I, the derivative of I di by dt, and the double derivative or the second derivative of I, that is this, each of these solutions, each of these values are part of the solution, and each of these values is multiplied by a certain constant. So this I is multiplied by this constant a2, a1 is pre-multiplied to this di by dt, and a0 is multiplied to this term d square by dt square. Okay, so when you have a2 times I plus a1 times di by dt plus a0 times d square I by dt square, they all add up to 0. So this is a special the special thing about this type of differential equations. So what is the solution of this equation? The solution of what do you mean by solution of a differential equation? The solution of a differential equation is that value of I which satisfies this equation, correct? This equation and this, all of this, right? So that is known as the solution of this equation. So if you have done differential equations before, you know that there is a special kind of a function used to treat functions like this. So I'll just mention it and I'll explain why I chose this type of a function. So we have discussed in the previous lectures that this exponential function e to the power x has a special feature that the derivative of this function is the function itself, right? So this e to the power x, or the exponential function, has this special feature that the derivative is equal to the function itself. So if we take that the solution of this equation, that is this differential equation, if we assume the solution to be I, that is some constant k times e to the power s of t, where k and s are constants which may be real, imaginary, or complex conjugates. So we will see each of these cases. Okay, so we have said that for differential equations of this format, we say that the best possible function or the solution is of this format. We'll see this. Okay, so if you take this I of t and you simply put this I of t in the above differential equation, what do you get? You get a square, a naught s square k e to the power st plus a1 s k e to the power st plus a2 e to, k e sorry plus a2 k e to the power st. All of this sums up to 0. Okay, now if you take out this factor k e to the power st, take a look at this factor, and there's a special thing about this factor is that this is never non-zero for finite t. For finite time, this factor is non-zero. K e to the power st is non-zero. So what does that mean? You can simply take out this factor k e to the power st here, here and here. You can simply take it out of the equation because this whole equation is equal to 0. So if this factor is not 0, what is the only thing that can be 0? That is this term. Is a0 s square plus a1s plus a2, right? So let me write this here. If I say that k e to the power st is non-zero, what is the only thing that can be 0? It is a0 s square plus a1s plus a2 equals to 0. Okay, so for this I is equal to k e to the power st to be the solution of the above differential equation, this equation must hold. Do you understand? For this differential equation, equation number 1, if we have equation number 2 as the solution, then the requirement is that equation 3 must hold. Okay. Now this equation, equation number 3, is a very useful equation and it's a very famous equation, and you will encounter it everywhere in your engineering course. This equation number 3 is known as the characteristic or auxiliary equation. Okay, this equation is known as the characteristic or the auxiliary equation. Now this is a quadratic equation. If you see quadratic equation, we mean any equation which has the power, highest power s, or whatever the variable, that is 2. That is why it's called a quadratic equation. So if s1 and s2 are the roots of this quadratic equation, what are they? These roots are minus a1 by 2 a0 plus minus 1 over 2 a0 a1 square minus 4 a0 a2, like this. Okay, so since the quadratic equation has 2 roots, the solution will have 2 forms. One of the solution will be I1, which is equal to k1 e to the power s1t, and the other will be I2, which is going to be equal to k2 e to the power s2t. Okay, now if I1 and I2 are each of the solutions of the differential equation. Let me call this let me give number to this, just a second. I'll call this equation number 3, I'll call this equation 4, then I'll call this equation 5, and I'll call this equation number 6. So if a1 and a2 are each solutions of the equation number 1, the sum of these two, that is, let's call it I3, I1 plus I2, is also a solution. How is it possible? You can simply, if you substitute the value of if you take this in the above differential equation, in the differential equation number 1, you simply get, if I take a naught d square I by dt square, if I write I2 plus I3 plus a1 d by dt of I1 plus I2 plus a2 I1 plus I2 is equal to 0, the solution is going to be like this. It's going to be k1 e to the power s1t plus k2 e to the power s2t. Okay, so this is the differential equation, the solution of the differential equation. All right, so now these terms, these s1 and s2, if I write them over here again, if this s1 and s2 are the roots of the quadratic equation, and if you take a look at this equation, what does this s1 and s2 term depend on? It depends on the only on the constants a1, a0, a0, a1, a0, a2. What are these a0, a1 and a2? These are the coefficients in the differential equation, right? So depending on the coefficients of the differential equation, we can make a statement: the magnitudes of coefficients a0, a1 and a2 determines the form of roots of the characteristic equation. Okay, so how does it determine the roots of the characteristic equation? Because if you see, this term, this part which is under the root, that is square root of a1, and let me write this as plus minus a1 square minus 4 a0 a2. The part under the radical, that is the part under the root, it may either be real, it may be 0, or it may be imaginary. Okay, depending on the value of a1 with respect to a0 and a2, right? And depending on the values of this a1, a0 and a1, a0, a1 and a2, we will have 3 different kinds of solutions. Okay, there will be one solution where a1 square is greater than 4 a0, or we can simply say that a1 square minus 4 a0 a2 is greater than 0. This will be one case. Another case will be when this a1 square minus 4 a0 a2 will be equal to 0. This will be another case. So in that case the radical is 0, right? And the third case will be that case where a1 square minus 4 a0 a2 will be less than equal to 0. Okay, so depending on each of these 3 cases, we will have 3 different kinds of solutions. Okay, so what can we make? What statement can we make? We make 3 different kinds of solutions. Okay, so how can we say that there will be 3 different kinds of solutions? Let's take an example. Okay, let's take an example. We have a circuit like this, which is connected like this. You have an inductor here. This is plus minus 1 volt. this is some factor K, this is 3 ohms, this is 1 ohm, and this is half of a farad. So let's write the KVL equation for I in the circuit. So what is this I? We can simply say that this is L di by dt, or if we simply go around the circuit, let me just write it for your simplicity. We can simply say minus V plus Ri plus L di by dt plus 1 over C integral I dt is equal to 0. Or if we adjust the values, arrange the values and put the appropriate values, we end up with and we differentiate this again to remove this integral sign, we will get the following equation. The equation is d square I by dt square plus 3 di by dt plus 2I equivalent to 0. Okay, so this is the differential equation. Now a very important tool for you to note is that depending on the order of the derivative, if I have di by dt, I will replace it with s, and if I have d square I by dt square, I'll replace it with s square. Similarly, if I have dni by dt n, it will be s raised power n. Okay, so we can substitute this s in the above equation, and what will we get then? The characteristic equation, this equation, if I get it here, it's going to be s square plus 3s plus 2 equals to 0. Okay, this is a simple quadratic term. Now what are the roots of this quadratic equation? If you see, the roots are s1 is minus 1 and s2 is equal to minus 2. Now we know these two roots. Okay, so what is the solution of the current going to be? Then we can simply say that the current or the solution of this equation I of t is some factor k1 e to the power s1t plus some another factor k2 e to the power s2t. Okay, so let's put in these values. So we are left with k1 e to the power minus t plus k2 e to the power minus 2t. This is I of t. So this is the general solution of this particular differential equation. What was the differential equation? This was the differential equation. So what is the particular general solution? This. Now what is needed to be calculated? We only need to find out these constants k1 and k2. Okay, and if you remember, and if you have been attending the previous classes regularly, how will we find this k1 and k2? We find this k1 and k2 by substituting for the initial conditions. Okay, initial conditions. Okay, now if I say that the circuit was previously unconnected and the switch was closed at t equal to 0, what can you say about the current I0? This current is equal to 0, since the current in an inductor cannot change instantaneously because there was no previous current. So current in an inductor cannot change instantaneously. Okay, so with this what do we get? We simply get this I0 plus is equal to 0. And if you take a look at the above equation, that is the original KVL equation for the circuit, that is this equation, Can you not find out the derivative di by dt at 0 plus, right? So let me write this here. So then di 0 plus by dt, since every other term is going to be 0, this is simply v by L, which is equal to 1 amp per second. Okay, so we have two initial conditions now, and if we substitute these initial conditions, that is, we substitute I0 plus is equal to 0, and if we substitute di 0 by dt in this equation 1, what do we get? We simply get that this k1 plus k2 is equal to 0, and minus k1 minus 2k2 equal to 1. How will we get this and this? We simply go to this equation and substitute for time t equal to 0, right? That is how we end up with these two equations, k1 plus k2 equal to 0 and minus k minus 2k2 is equal to 1. So after we solve these two equations, we get k is equal to plus 1 and k2 is equal to minus 1. Okay, so with this, after we put this in the equation here, we end up with the following solution. This is the particular solution for the differential equation. This is the okay. So this is you can easily verify that if at t equal to 0, what is the current? It is simply going to be equal to 0, right? And if you put in the this same value in the differential equation, that is this, you will again get that the differential equation, not here, but if you put the values in this equation, you will simply see that this equation holds. Okay, so this is one type of a case where the roots S1 and S2, what were the roots here? These S1 and S2 were real roots for a quadratic equation. Okay, so this is about systems with real roots. Okay, in another case we will see where there are equal roots, and these are real and distinct roots. Real and distinct roots, because one root was what? We had S1 equal to minus 1 and the other root was S1 equal to minus 2. So these were real roots, they were real numbers but distinct. S1 was not equal to S2. So this is one kind of a case, one case where they are real and distinct. In the next video, in the next class, we will see the case where there are real but equal roots. That will be another case. And in the last case, we will see where there will be complex conjugate roots. Okay, that will be the topic for another class. Okay, so I hope you have understood this, and in the next class we will talk about the second type of solutions. So thank you, and I'll see you in the next class.